Hello there, Mr. Sutton with the AB Calculus 613 classwork answers on volume with solids of revolution. For this problem, we're told that we have a vase with a shape obtained by revolving the curve 2 plus sine of x from 0 to 5 around the x-axis. We want to know the volume in cubic inches, like it matters because they're giving us the units, of the vase. All right, so for this one, because we're just taking the area under 2 plus sine of x and revolving it around the x-axis, we have no separation, no space between our area and the axis of revolution. That means we can use discs on this one. So we'll use the cross-section given by area of pi r squared. The r value in this case is just this 2 plus sine of x function. So we're going to just call this pi times 2 plus sine of x quantity squared. And now I just need to take this area, this cross-section area, and integrate it from 0 to 5. So that's going to be volume equaling integral from 0 to 5 of a of x dx. And now let me just put all this in the calculator. So just to make things a little easier on myself, I've entered my area function, pi times 2 plus sine of x squared, in the y1. And now I'll just go out and math 9 this one, integral from 0 to 5. And I'm just going to do alpha trace y1 now, because that's where I stored a of x dx. Enter. And I get 80.115, which gives me answer choice E. On this no calculator problem, they're telling us R is the region between the graphs of y equals 1 and y equals sine of x, between 0 and pi over 2. The volume obtained by revolving this region around the x-axis is given by which expression? So the good news is it's no calculator question, so you don't actually have to evaluate any of this. The bad news is you kind of need a visual to see what you're dealing with. So you can graph the horizontal line y equals 1. Graphing sine of x, you should also be able to do that. It looks something like this. And yeah, I got this off of my grapher, but you could graph this by hand if you needed to. So sine, we know, starts at 0 and reaches its highest height of 1 when you get to a value of pi over 2. So that's where these are intersecting. Pi over 2 is the intersection between y equals 1 and sine of x. So our integral then is going to be going from 0 to pi over 2. So we'll put that in later, but let's also get the area function that we're revolving. Now you can see here that there's some space between my region here, my area, and the axis of revolution, the x-axis. Because of that, we're going to need to use washers or donuts as the model for my cross-section area. So I'm going to have to go with pi, or area equals pi times big R squared minus little r squared. Now I have to actually express this in terms of x as well. The outer radius here, the radius further away from the axis of revolution, is just the line y equals 1. So that's going to be 1 squared for r squared. For little r, we've got the inner radius here, sine, the closest radius, closest distance away from the x-axis. So this is going to be minus sine squared of x. And now I'm going to put all of this inside an integral. So I'm going to say that my volume is going to be pi. I'm just going to take this pi out of the integral. And why did I do that? Well, I see it in all the answer choices. Otherwise, I'd leave it in a little longer. So we have pi times the integral from 0 to pi over 2, which all the answer choices have that as well. So far, this doesn't narrow things down a whole lot. But now inside, we're going to have this 1 minus sine squared of x stuff. Now let's see if there's an answer choice for that. I mean, if they were really mean, they would turn this into cosine squared of x and kind of hide it. But if you look up here, we do actually have one that has 1 minus sine squared of x with a pi outside. And it's not this one. This one's pretty close, but this is squaring everything by multiplying everything by itself. We actually need, let's see here, choice E has what we're looking for. For this problem, we want to find this volume of the solid revolution that I get when I take the area between radical x plus 2, y equals 0, which is the x-axis, and the vertical lines x equals -1 and x equals 7. Take all this and revolve it around the x-axis. This is a grapher problem, so I'm going to start by actually graphing all this out. So I've got my y equals square root of x plus 2 entered in my y1. Let me zoom 6 that thing just to get a basic idea of what I'm dealing with. And now let me put in my vertical lines. So I'll quit out here. I'll do second program to give me my draw menu, option 4 for vertical lines. I've got -1 is the first one, x equals -1. There it is. And let me quit out again and just do that again, but this time I'm going to enter in 7 instead of 1. And there's my other vertical line. So this is what I have on my grapher. I'm taking this region in here, revolving it around the x-axis. I can see there is no space between the area that I'm revolving and the axis of revolution. That means that I can use disks rather than washers. So my cross-section area, I'm going to write as a of x equals pi r squared, just using disks here. And then for my r value, that's just going to be the distance from the x-axis to this upper limit here, this square root of x plus 2. So I've got pi times radical x plus 2 quantity squared. And yeah, that really is just pi times x plus 2. But I'm not going to bother writing that because I'm about to put all this in my calculator anyway. So my volume then is going to be the integral from -1 to 7 of a of x dx. And now it's time for the calculator. To make things a little bit easier on myself, I'm going to go into y2 and basically put this function in there. So we've got pi, and I'm multiplying that by essentially what I put in y1 squared. I'm just going to do alpha trace y1 and square that. And now let me get out of there and do math 9. And I mean, this wasn't the only way to do it, but I just like using the y function so I don't have to worry about parentheses. So we're going from -1 to 7, alpha trace y2, that's where I put my area function, dx, and that comes out to 125.664. For this problem, I want to take the area between this parabola and y equals 1 and revolve it around the x-axis. Let me start by actually graphing this out to see what I'm dealing with. So I've got my two functions here entered in my y equals. Let me do zoom 6 to see essentially what this looks like. So there's the parabola, there's the line. So I just want this area in here. And if you zoom in, this is a closer look at what it actually looks like. So these intersect at where? Well, let me figure that out. So one thing I'm going to do right away actually is I'm going to rename this parabola as just f of x. And I'm going to set that equal to 1 because I want to find out where these things intersect. Now I could do this on the calculator. It definitely looks like I'm intersecting at 0 and 2. But just to be crazy, I'm going to do this by hand. So let me subtract 1 from both sides. And I can factor an x out of x squared minus 2x. And yes, indeed, x equals 0 and x equals 2 are my points of intersection. Groovy. So now I need the integral from 0 to 2 of what? Well, at this point, we better get our area function that we're going to be integrating from 0 to 2. Now, since I'm integrating this area around the x-axis, and there's space between my bounded region and my x-axis, that means I'm going to have to use washers because I've got this hollowed out stuff here. So I'm going to use a of x equals pi times big R squared minus little r squared. For big R, that's going to be the side that's further away from the axis of revolution. So that's just the line y equals 1. So I'm going to write pi times 1 squared. And then little r, that's going to be the inner part of this bounded region represented by this function up here, x squared minus 2x plus 1. Rather than writing all that and squaring it, though, I'm just going to square f of x because I renamed this to be f of x. So minus f of x squared. And now I'm going to take the integral from 0 to 2 of this a of x function, dx. Time for the calculator. To make things a little bit nicer for myself, I'm going to go back to my y equals now and actually put this area function in here. So I've got pi, parentheses, and 1 squared is just 1, minus, well, I stored my f of x function in y1, so I'm going to just do alpha trace y1 and square that. That's kind of nice. Close my parentheses. And now let me actually just quit out of here and do my integral. So I've got math 9 going from, let's see here, we said 0 to 2. And now I stored a of x in y3, so alpha trace y3 dx, enter, 5.027. For this free response problem, we're given this region R in the graph up here. It's in the first quadrant, and they're telling us that we've got the graphs 8x cubed, or f of x is going to be that, and also the graph g of x equals sine of pi times x. And they don't really tell us which one is which, but if you think about what these actually look like, this top function here is going to be your sine function. This is g of x up here. And this other one down here, this is your cubic function. This is the other part of the cubic function above the x-axis. All right, so we want to start by writing an equation for our line tangent to our graph of f. So again, that's going to be this bottom function here at x equals 1/2. Now they were kind of nice to us, and they gave us the intersection point 1/2 comma 1. So we know that f of 1/2 is going to be 1, but we're still going to need f prime. Before we do any of that, though, let me get my basic setup here. So I'm going to write L of x equals, and then I'll do my tangent line dance here. So I'm going to have f of 1/2 plus f prime of 1/2 times x minus 1/2. Now I just have to figure out the values of f of 1/2 and f prime of 1/2, plug them in, and that gives me an instant tangent line equation. So we said f of 1 was 1. They gave that to us up here. But if you wanted to actually calculate it out, you could. It's just 8 times 1/2 cubed, or 8 times 1/8, which again is 1. All right, how about f prime? So f prime of x is going to be 24x squared. Plugging 1/2 into that, I have 24 times 1/2 squared. That's 24 times 1/4, or 6. You didn't have to simplify it, but I did just because. So let's plug all that back in now. We have L of x equals, this is now going to be 1 plus 6 times x minus 1/2. And there's our tangent line. For this part of the problem, they just want us to find the area of R. The catch is that this is a no calculator problem, so we're going to have to do this by hand. Let's start by setting up our integral. So we know that this integral has to go from 0 to 1/2, because that's the intersection x value. So I'm going to have the integral from 0 to 1/2 of, now I need to do top minus bottom. The top function again was this sine function, g of x. So I'm going to have sine of pi x minus 8x cubed, all that with a dx outside. Doing this by hand, let me take my antiderivative. Antiderivative of sine of pi x, that is going to be negative cosine of pi x times 1 over pi. We have to divide by that inner tail. And we're also going to have antiderivative of negative 8x cubed. That bumps up to an exponent of 4. Dividing by that, we have negative 2x to the 4th. All of this evaluated from 0 to 1/2. So I've got all of this stuff with 1/2 plugged in for x. That looks lovely. Minus all this stuff with 0 plugged in for x. And you're actually done when you get to this part of the problem because you've got all constants. But if you want to be brave and simplify for absolutely no reason whatsoever on a free response, let's see what happens. So over here, this actually looks a lot worse than it is. This is cosine of pi over 2. That's the x value at the top of the unit circle. That's just 0. So this whole first term is gone. That just leaves us in this bracket here with negative 2 times 1 over 16. That's negative 1/8 when the dust settles. Coming over to this other one, 2 times 0 to the 4th is obviously just 0. So now we just have to really worry about cosine of 0 times negative 1 over pi. Well, cosine of 0 is just 1. So this is going to be minus 1 over pi, or just plus 1 over pi. And we could probably go even further, but I'm not going to. So I'm calling this done. For this one, they want us to write, but not evaluate, an integral expression that gives us the volume when we revolve this around the line y equals 1. The first thing I'm going to do is draw that line right up here. So now I see that I'm going around something that's above the bounded region, so I'm going to have to factor that in. And also I see that I've got some space between my area and the axis of revolution. Because I have this space in here, that tells me I'm going to need donuts or washers for my cross sections. So I'll start with the formula a of x equals pi times big R squared minus little r squared. I don't get anything for actually writing this, but it at least gives me a place to put the things I'm about to figure out next. So now I need to actually figure out big R and little r. big R is just the distance between my axis of revolution and the outer part of the area. It's the big radius. So that's going to be 1 minus whatever this bottom curve was. This was 8x cubed, which you could also call f of x. So I'm going to write pi times, and in parentheses, 1 minus f of x quantity squared. Now I have to subtract the little radius squared. That's going to be 1 minus this inner function, so 1 minus g of x, and I'll square that and subtract it from what I already have. So this gives me the area of my cross-sections. But I have to write an integral that uses this. So I'm going to write volume equals the integral from 0 to x equals 1/2 of, well, this stuff here. But I'm not going to bother rewriting this because I already told you this is what a of x represents. I'm just going to write a of x dx in there, and now I'm done.